Chinese Academy of Sciences. I think after Antonia's talk, I'm thinking whether I should persuade the students to change his topics to GAN-based methods. Just the fantastic results. For this paper, we are trying to address a robust wheel tracking problem. We propose a relation-aware multiple attention Siamese network for wheel tracking. So for wheel tracking, the problem is defined as in first frame, we define a target, and then in the subsequent frames, we needed to track the target. And there are a lot of challenges in wheel object tracking, including the object might have a very large deformation. Also, maybe the object is occluded, or there's a very large rotation, and sometimes there are some very similar objects which will distract the object tracker. In this paper, we try to address the partial occlusion problem. For this problem, there have been a lot of methods on trying to solve this problem by explicitly dividing the object with some predefined grid into multiple parts or multiple cells, and we try to think whether can we learn some adaptive schema to automatically localize discriminative parts of the target. It's showing in this picture. And we also think we should consider the part dependency. Therefore, we need to consider the other parts when we try to represent one of the part. So this is the main motivation of the proposed method in this work. We base our method on a new RPN network published in CPR last year. In this RPN network, they try to use Xilin to extract the features of both the template and the search region, and then finally use the correlation to compute the classification and regression for the tracking. Based on this framework, we proposed our relation-aware multiple attention Psi RPN. In our work, we also use Xilin to extract feature, but then we use some network to compute multiple attention maps. For each attention map, we try to model one of the parts of the object, and then we further model the attention map by considering the relationships between different parts, and finally we use the similar method as in the SAM RPN network to complete the tracking problem. So for our method, we have two key components. One is the multiple attention module, and the other is the relation-aware compensation part. In the following, I will introduce them separately. For the first key component, that is the multiple attention map learning, we try to represent each part of the object using attention map. For this, we based on the same feature, and in one branch we use a one-by-one convolution layer to get the compact feature, and at the same time we use another one-by-one convolution layer to get the multiple attention maps. And then we modify or improve the feature by combining the attention maps and the feature together to get the part feature maps. In order to encourage the diversity of the attention maps, we introduced an orthogonal constraint by using this term here. Basically, we try to make the attention maps diverse among these different attention maps. And after we get the multiple attention maps, we try to further model the relationship between different parts modeled by the attention maps. The reason is that if we use a single part, as we can see that if we use only a single or a very small part, there might be many similar patterns in the background, which might attract the part into the background. Therefore, the tracker will drift to background cluster. So, in our method, we further enhance the part features by dot mapping the aggregated global feature. Here it's DI that considers the features of the other part by using this equation. This is the feature of the part features, and DI is a global feature consider the other part, and DI is computed by using an operator working on the input feature, and also affinity matrix SI. For the SI is computed by using also operator. Specifically, phi and rho is the embedding phase, the embedding function implemented by one group convolution layer, followed by global average pooling, and reshape the operator into a image shape. And we use the number of the groups equals to the number of parts. As I have mentioned, S bar actually forms an affinity matrix. Rho is similarly another one-by-one group convolution layer after with the reshape operation. Then in the following, I will introduce the evaluation results of our method. In all the experiments, we use VID and the YouTube BB dataset as the training data for fair comparison. Please notice that our method is not an online learning method. We actually do offline training. And there's no online learning, so the method can work very fast. As we know, Science RPM can track objects in about 200 frames per second. Our method is slightly slower than Sci RPM. It's about 180 frames per second, and we measure the accuracy of the tracking by using EAO, that is the expected average overlap. First on the VOT 16, as you can see, compared with the Sci RPN, our method is the EOA of our method is obviously better than the Sci RPN. And on the VOT 2017, on the 1660 videos, our method can also work much better than the Sci RPN. We also evaluated our method on the OTB 2015 there are 100 videos, as you can see from the comparisons in this figure. Our method also outperforms other comparative methods. And another experiment is conducted on the IOA sort dataset, and the success rate of our method is also better than the other comparison methods. And another experiment is conducted on the more than 500 videos in the tracking net, and we compared with the MD net, and our method is the AUC that is an area under curve measurement is also better than the MD net and the SAM FC net. We also do ablation analysis. As you can see, if we use only the multiple attention mechanism, we can achieve better results than compared with the SAM RPN method. And if we add the I think it's orthogonal orthogonal constraints, we can get a little better results. And if we add the relation aware part, then we can get much higher tracking accuracy. And finally, if we add all the components, then we can get the final results better than other methods. And I will show you some tracking results here. As you can see, the green rectangle is the ground truth, and the red one is ours, and the blue one is the SAM RPN result. As you can see, especially if there's occlusion, our method can achieve better results. Okay, so a very short summary. We proposed a relation-aware multiple attention Siamese network for robust real tracking, and we showed that both the multiple attention mechanism and the relation-aware module contribute to the accuracy improvement, and our method can achieve a very fast speed, only slightly slower than the same SAM RPN baseline. Okay, thank you for your attention.
Okay, are there any questions? Any questions from room 104?
No, it doesn't look like it.
Okay, I think as you're running late, we'll move quickly on to the next talks. Can you thank the speaker again, please, and can speak in the
Thank you.
Are you Ebrahim here?
Yes.
Okay, so hello? 1, 2. Okay, so the second talk is Spatial Transformer Spectral Kernels for Deformable Image Registration, and it's being presented by Ebrahim al-Safadi.
Hi, good morning, everybody. I'm a data scientist at Amazon and their imaging technologies division in Washington, in Seattle, Washington. I'd just like to mention very briefly that we are looking for people who are interested in ray tracing problems. If you are interested in problems where you have 2 snapshots of an image of a chair and you'd like to convert it into 3D and all sorts of different images, do please consider applying to the UK office or our cooler office in Washington. Our problem, so this is related to my PhD work at OHSU with my advisor, Xubo Song. And I should actually say this is part 1 of our work, and it's related to transforming the spatial domain of one image to the other one. So it looks like something like this. So let's say you have 2 images. A is the original one, B is the deformed one. And this application comes up a lot in medical applications where, for instance, you have a motion compensation, somebody is breathing, or you have a brain tumor and you're looking at the image at one instant in time and then comparing the tumor shape 2 years later on. And you'd like to find a spatial transformation, so something like this, D. You're trying to infer, by looking at the 2 images at the top, you're trying to infer the deformation field at the bottom. So it is a challenging problem because you're not operating on the actual pixels, you're inferring some transformation in the background. Okay, so I'll quickly talk about the actual spatial transformation and then about a very important component that's usually neglected in image registration problems, which is interpolation. And we have to credit the authors of spatial transformer networks at Google because they really brought this problem to the forefront in their spatial transformer network models. And I'll talk very briefly about the different types of kernels that we used for this type of application. All right, so this is the general problem. If we want to formalize that mathematically, we're going to talk about how are we going to minimize the dissimilarity between the 2 images. And if you can see the actual, you can't, here it is. So we have 2 images, I and J, and what we would like to operate on is X. So the pixels. We're not actually operating on the intensity values of the images. We're operating on the pixel values. And the main challenge being that, well, you can have an infinite amount of transformations. Which one actually is going to, it's a highly ill-posed problem, and regularization is going to be the most important challenge. Let me show you a very simple example. This is a toy example. Let's say you have an image like this, and you want to do some transformation, and the main thing being the transformation on the pixel value. So let's say you've done something like this type of very basic transformation. Now you want to compare. You have your dissimilarity function between I and J, right? But you can't really compare them because now this image, you've already transformed its pixel locations to real values, right? They're no longer on a digital image. They're no longer on a digital grid. So you'll have to resample your image. And once you resample, you're going to violate the main condition in classical image registration theory, which is that you've actually played with the intensity values, where by traditional image registration, you're not supposed to do something like that. So you're going to either use, for instance, nearest neighbors, or you're going to use cubic. And notice in both cases, you've actually changed your image. So when you're computing the dissimilarity metric, your optimizer actually changed. You're going to converge to a different location of your pixels based on this resampling. Okay, so this is quite problematic in practice. So the Google team did actually bring this into the forefront, and they did derive a closed form solution. So when you're doing backpropagation, you do it through 2 things. One, through your interpolation, and they use a very simple interpolator at that case. They just use bilinear interpolation. And if I remember correctly, they also used nearest neighbors. And then they used a different part of the model to actually define the transformation. So they use convnets. We're not using any. Just to answer a question that I was asked in the poster session, there is no deep learning involved here whatsoever. It's pure kernels. Okay, so now let's go to the actual transformation. The upshot here is to say that, okay, we're going to refine these transformations. There's an infinite amount of transformations. We're going to do a clever trick, and we're going to say the transformation has to live in a reproducing kernel Hilbert space. And by that, you're going to have a tremendous amount of very nice theory and theoretical properties. If you remember things from SVMs and all the representer theorems that came with kernel methods back in the 90s, it would say that if you actually confined your transformation to live in RKHS, then it would be, you can express your transformation as a linear superposition of these reproducing kernels. What type of kernels? Anything, as long as it's positive definite. So it's a very generic framework. And then once you do that, you can go through details in the paper to see how we can finally derive something like this, equation number 4. And notice the most important thing is that the transformation itself is going to be this linear transformation multiplied by this vector. And all we need to do is find this vector. The huge kernel matrix is pre-computed once before it goes into the gradient search or any optimizer. So that's one interesting property. It's huge, of course. If you look at that matrix, you're actually looking at, of course, you know that kernels scale very poorly with data that's quadratic. So we're going to look, in the general setting, you're going to look at the distance between every pixel and every other pixel, which is huge. You can parameterize the problem and look at control points. The control points also being very generic because you don't have to confine yourself to a finite grid or to a uniform grid. But let's just take the simplest case here and do something like this. So we're only going to manipulate the red points, the red grid, and then once you do that, the kernel transformation is going to do all the rest for you. And here we've used the most basic kernel, an RBF kernel. I'll show later that this is fairly generic. You don't have to confine yourself to RBF kernels. Once you do that, now you've transformed your image, right? You're outside the digital domain. How do you go back? You're going to do resampling. So define a very generic interpolation function, psi. So it's going to take an input, your image, the intensity values, and then the pixels that you already know, the digital domain that you know, and the locations that you're going to interpolate from. So this is going to be your interpolation function, and then you plug everything back in. So you have your spatial transformation and your interpolation function, and that all goes into equation number 9. And so if you compare what we started with, this is what you're going to see in image registration or nonlinear alignment image papers. It's equation 10. So after plugging everything in, things become much more concrete. There's no longer a group transformation and all that. It's just going to be, you have your interpolation function applied to an image that has been transformed in terms of its pixels, and all the entire problem now reduces to finding theta, which is a very small subset of what we started with to begin with. And you can use run-of-the-mill gradient descent, Adam optimizers, or so forth, any like momentum method or any optimizer. We use FGS and gradient descent for this purpose. I don't need to go into the math except for saying one thing. Since you have this in equation 11, you can see that that's just a linear transform. So if you just substitute it into a single matrix M and you want to do a gradient descent through it, it just flows directly. And all you have to do is then find the derivative of your interpolation function, and then the interpolation through the kernel becomes very straightforward. And so notice here the very last equation that this is very generic. It's much more general than what was done in the Spatial Transformer Network paper. You can see that it's for any generic interpolation function. So you can use B-spline, Nadaraya-Watson filters, which we use because they consistently gave better performance than other interpolation functions. And then it's also for any generic kernel function. So what if we don't want to confine ourselves with RBF? Since RBF are very rigid, let me show you something like this. So RBF, for instance, you know that any two distances in an image are going to give you exactly the same kernel distance, right? So it's very rigid. There's recent work in GSM kernels, for instance. They're called the generalized spectral mixture kernels. So we can use that, and they're extremely powerful because now you can play with how rigid your transformation is at different parts of the image. So notice, for instance, C is your RBF, your run-of-the-mill kernel, so it's very rigid. So here to here at different corners of the image is going to give you exactly the same dynamics. This doesn't have to be the case. You can change your dynamics depending on where you are in the image by changing the profile of this type of kernel. And I'll give a very basic example of, we had several experiments mentioned in the paper. I'll only go through one. It's a liver image. We actually created the spatiotemporal field of somebody that's breathing. So there's a liver image. I don't have the video with me here, but we simulated a pattern of 8 snapshots of somebody breathing. And what we're trying to do is do some motion compensation to track, for instance, a tumor, location, and so forth. And here, the name of the game is actually very high accuracy. These applications are in computational anatomy, and it's not just detecting the tumor. It's also finding what is the most accurate transformation through the entire grid. So even for anatomy where there's like developmental psychology and you're seeing the growth of the brain. It's not just tracking the position of one particular thing, but you're actually tracking the growth of the entire brain as it moves in time, in a matter of months or years. Okay, so the original image is I in this case. J is one sample of the transformed one. J tilde is the one after compensation. So you can look at the green images. I think that's the clearest one. G is the differences between them, the intricate differences right at the beginning before registration. H is the one after registration. So you can see that we've successfully did it by manipulating only the pixel background, only the deformation field. And so if you compare the actual distances here, you still see that there is some error. There are more advanced methods called LDDMM methods in computational anatomy. So those will definitely reduce the error by a smaller amount. However, since we've created artificial problems of like when we simulated the actual background field, so we know exactly where the background field is, which is the real ground truth. It's not the actual intensities of the images. In that case, so you can see that the intensity values of RDMM methods like sine, symmetric normalization, the last row, it does give the lowest RSSD, which is what we expect. However, when you look at the deformation field, so here the ones highlighted, you can see that the correlation with with the actual grid field in our case is higher by 3%. So they had a correlation of 79.5. We had 82 using this kernel technique, and this is the spatial temporal field that we had here in the bottom. And in conclusion, this does provide it is a very promising direction of work. We're currently in the step of doing or like deepifying this or kernelizing spatial transformer networks, because spatial transformer networks are very easy transformation models. They use affine transformations, only 6 parameters, whereas these here you're talking about hundreds of parameters, if not thousands. And one aspect of this still that we have to go over is that it's quite complex because you need to evaluate a gradient for a matrix that's about n by n. So it scales by the number of pixels, by the number of grid points. So that's still a bit too much. So we're in the process also of having rank 1 approximations for that, and using deep learning to improve also the actual spatial transformation. And that's about it. Thank you.
Okay, do you have any questions? One there?
Thank you. Thanks for the presentation. Question, so you said the theta is in the hundreds or thousands of parameters?
Yes.
How do you choose that size?
Performance versus computation. So honestly, like, if we started with 64 by 64 and it ran for a very long time, and then we tried 32 by 32 and we got very close performance, we just stuck with 32. And at the end of the day, we did notice that 16 by 16 was giving, like there was this curve, the SNE curve, where beyond 16 by 16, we weren't capturing too much while the computational time was growing non-linearly. So that's when we stopped either at 16 by 16 or 32 by 32. Thank you.
Further question there?
Thanks for the talk.
Thank you.
But just a couple of questions. The interpolation problem, you really showed that it's important to solve for the interpolation, but doesn't it go away if you go higher resolution images? And then obviously you're doing the transformation in 2D, and you're also using the image brightness constraint, that the brightness of a pixel should not change. When do you find these assumptions are violated?
Thank you. Yeah. So first question is very important because yes, of course, if you increase the resolution, you do resolve a few of these problems. But computationally, they are very demanding. So the bottleneck of this is resampling. A lot of like a good percentage of the time of these algorithms when they're running is having to go through the resampling procedure every time. If you're doing gradient descent, you do have some research where people try to avoid doing this resampling because it is computationally intensive. So Yes, in a way it does, but then with this computational aspect of things, I think it is important to use. When we did the Nadara Watson filter, it just performed much better than other ones. And yeah, so your second question was about 2D to 3D. Yes, we still haven't applied it to 3D in this case. It is still computationally intensive, so that is one issue that we are currently working. One thing that I do mention in this regard is that you can have a Kronecker decomposition. So if you're using RBF, so that's one aspect, one nice aspect of using RBF. It's a simpler kernel, but then you can very easily decompose the problem and just becomes a tensor product, and that becomes nice. We're using GSM kernels as well, and that doesn't break in as easily. So that's one issue where we'd like to still gain the theoretical properties of having more advanced kernels, but then at the end of the day, if you want if you want a very practical setting, then we are yeah, we'll have to reduce that computation time.
Thank you. Do you have any questions from room 104?
No, there's nothing from this side.
Okay, in which case we move on to the third talk.
Thank you.
Okay, so we seem to have a rather blessed session here, in that the next two papers actually won the best paper prizes last night. The first one being the best student paper. So we got Ardhendu, Tripathi. Come in. Oh, yeah, ready? Okay. Which is tracking the unknown and the unknown by leveraging semantic information.
Thank you for the introduction. I am Ardhendu Shekhar Tripathi. I'm a first-year PhD student at ETH Zurich in the Computer Vision Lab. And I'm going to present my work titled Tracking Known and the Unknown by Leveraging Semantic Information. This work was done in collaboration with Martin Danelljan, Radu Timofte, and Luke van Gool. So the aim of generic visual tracking is to track arbitrary objects which are unknown beforehand, and those objects may include uncommon objects like surfboards, exit signs, or common objects like people, cars. Current trackers don't actually integrate the class information into the tracking pipeline, which we think could be pretty pivotal going forward, especially in the case of common objects like people and cars. On the other hand, for multi-object tracking, those paradigms target object-specific tracking. They have pre-learned target detectors and motion models which work in this case. And a drawback, though, is that they can't track arbitrary objects. For example, like if a paradigm was trained to just track humans, it can't track objects which were objects which are arbitrary or which were not in the training set. For example, if they come across cars, etc. So our aim here is to integrate semantic information and leverage it during both test and train times, and at the same time maintain the generic nature of the tracker so as to, like, without having an information of what kind of object we are tracking, we want to integrate that information and then go forward. So in this work, we propose an end-to-end tracker which leverages semantic information at both inference and test times. Moreover, this tracker, we aim that this tracker works in both the scenarios. One, when the class is known during tracking. For example, if we know that we are trying to track a human, or we are trying to track a car, we're trying to track a cup, or if it is unknown, for example, if we are just given a bounding box, we just need to somehow integrate the information that, okay, this is a cup, and we need to integrate that information in the tracking pipeline. So for the architecture overview, given the bounding box in the first frame, the target model predictor first extracts the appearance model from the bounding box, and we get a target filter which is used by the tracking module for the inference frame to predict the final bounding box. This is what happens for general trackers, but here in this work we integrate semantic information into the tracking pipeline. So if the class is unknown, we directly feed it into the tracking module. If the class is if the class is known, we feed it directly into the tracking module, and if the class is unknown, we have a semantic classifier which basically predicts what kind of object you're trying to track, and then it feeds it into the tracking module, and then the tracking module goes on doing its work. So the tracking module has two components, the target classification and target estimation. So target classification. So target classification is basically localizing the object in the frame, so where the object is. So first, using the target filter, we get a target appearance-based detection score. Next, we also have semantic information integrated into the semantic detector module, where we train class-specific filters offline, and those class-specific filters then go on to give different detection scores for different kinds of objects. For example, a channel would signify a detection score map for a person, for a dog, etc., etc. And then the semantic classifier is used to just choose which channel. So, for example, if the semantic classifier gives a high score for a dog, that channel would be chosen. In case of in the case where the object is known, this semantic classifier would not give a probability distribution, but it would be a one-hot vector, which then would be used to choose the channel. We further train a fusion module where we fuse both the scores. It's a weighted sum of both the scores, and these weights are trained offline to make the system more robust, which finally gives us the final detection scores, which are used to localize the object in the frame. We also propose an online version of our approach. So for our end-to-end tracker, the target filter was extracted from the first frame. Moreover, as time goes, the appearance of the object may change, and it may be pretty pivotal to change the encoded appearance of the object in the target filter. So we use the optimizer used in the Atom tracker to update the target filter, which is learned online using the optimizer that is proposed in Atom. So once we have the location of the object, where the object is in the frame, we need to define an accurate bounding box around the object. So the aim of the target estimation module is to define the sampled random bounding boxes around the localized objects during inference. We use the appearance-based IUUNet module that was again used in Atom. The IUUNet module basically predicts the intersection over union for each sampled bounding box. So for training, we use 4 datasets. The train split of 4 datasets: the GOT10K dataset, the COCO dataset, the TrackingNet dataset, and the LaSource dataset. The important thing about all these datasets is these datasets contain meta information. For example, what kind of object you are tracking, what kind of motion it is, though we don't exploit what kind of motion it is, but we exploit what kind of object it is. And so for training, during training, the image pairs are sampled in the same way as in Atom and in the Atom tracker and Siamese based trackers. So we consider 25 object classes which are based on the parent class list of the ImageNet dataset. We also have a additional other class which takes over when the object belongs to none of the classes which are predefined. So to test the effectiveness of each of our components, we also perform an ablation study on 3 datasets. We measure the performance of our algorithm using the area under the curve measure, which is basically the integral of the overlap precision curve. So as a baseline, we don't use any semantic information during training or during inference, and which is basically this baseline basically resembles the Siamese tracking pipeline. So starting with just using semantic information during training, that is using it as an auxiliary task, using the semantic classifier and training the architecture with the semantic detector, we get a huge boost in the performance. Further, when we use the semantic detector scores and fuse it with the with the target appearance-based score using the fusion module, which is also learned offline, we get further improvement. One important thing that we noticed was if we know the class, we don't get much boost in the performance of the tracker. So we investigated it, and then we found out that our semantic classifier was pretty strong. It achieved an accuracy of around 94%, a top one accuracy of about around 94%. So for some quantitative results, this figure shows the success plot for various trackers on the Lasso test split. Ours here is the end-to-end trained architecture, and ours OL is the version of our approach that involves the online learning. Both versions of our approach basically outperform Atom and other trackers with a significant margin. They set a new state of the art on this data set. So this table shows the results on the VOT data set, the visual object tracking data set. Here, even after using a shallower network, a ResNet 18 network for feature extraction, as compared to the ResNet 50, which was used by the CMRPN++, we get comparable results in terms of expected average overlap. On the other hand, for robustness, our tracker is more robust. We've also tried our tracker with the ResNet 50 network, and it outperforms CMRPN++ in that case on this dataset and one more dataset which is in the paper. So now the qualitative results. So both the trackers perform pretty well when there's occlusion involved. CMRPN++ and Atom sometimes fail. They are not able to come back and track the object back. So again, there's occlusion, and both our trackers perform pretty well there as well. Even for target estimation, so when we use semantic information, the target bounding boxes are learned pretty well, and we are able to define perfect bounding boxes. So in conclusion, we propose an end-to-end trainable architecture for visual tracking that exploits available semantic class information during both training and testing. Our tracker can operate in the case where when the object class is unknown. That is where the semantic classifier comes into play, while also capable of benefiting from semantic information which is available in a multitude of real-world scenarios. Thank you.
Okay, so do we have any questions? So no questions here. Do you have any questions in 104?
No, there's nothing on this side either.
You said no, did you? It's quite. Okay, we're doing for time. Okay, in the age of catching up, we'll have the last talk. You are Axel here?
Yes. There you go. All right.
Brilliant. Okay, so I forgot, maybe we should just congratulate the last speaker for the best student prize. And I don't know how this happened. This is completely at random because of the prize. We have the best science paper prize coming up as the last talk of the session. So congratulations.
Thank you.
Okay, so without further ado, this is Tracking Holistic Object Representations. This is by Axel Sauer and the rest from Technical University Munich.
All right.
Okay, yeah.
Thanks for the intro. Okay, so last talk this session, so I hope all of you have some attention left still. My name is Axel Sauer. I am from TU Munich. I'm going to talk about tracking holistic object representations. This is joint work together with Eli Al-Shabut and Sami Haddadin. And first off, visual object tracking, I want to tell you what the current state of the art is and what current problems are. So, and as you've seen before in the talks, like commonly it's solved by doing template matching, where you have one input image, and in the beginning of the sequence you are given the coordinates of the bounding box surrounding the object that you're supposed to track. So from this you extract a template image. So this you feed into a tracker, and out comes the prediction. So if you lift up the hood of the tracker, how it's usually done, you have one encoder, you encode both images into one feature space. There you do a dot product to compute similarities, so a activation map. And like recently there has been a shift towards using Siamese networks for the encoding, and then the dot product corresponds to computing a convolution in feature space. So based on this activation map, depends on the tracker how it's done, but you get a bounding box which then is used for the prediction, and on it goes through the sequence. So the current state-of-the-art trackers are able to track objects really well at high frequencies, as you can see. Although, however, if the appearance of the object changes like quite drastically, in this case, it's a change in texture, but it can be also like change because of rotation or illumination or whatever you want to have. And current state-of-the-art trackers use one single template. So obvious solution would be we use multiple templates, right? So, but there's a reason why current state-of-the-art trackers use only one template that is given in the beginning as ground truth. And introducing multiple templates, we introduce several problems also. So for one, it's slower. Of course, you have more computation that you need to do. So also, usually it's tracker specific, so you need to adapt your whole structure of the tracker in order to take multiple templates. Also, in most cases you need extra training, so you can think of having an extra neural network to either pick templates that you use for tracking, or some approaches to something like learning a residual template and then you modulate your previous template with this residual. Of course, if you have a neural network, you have to train it. So, and then in these approaches that I just described, both of them lack interpretability. So there's not really a good way to tell why certain templates were picked. Or in the case of residual templates, you can look at the residual template, doesn't really make sense visually. Also, you add complexity and hyperparameters to the system, which is always bad, of course. And you can introduce drift, since you're not fully guaranteed that you still have the object throughout the sequence, since you want to take in new information, and this is not ground truth necessarily anymore. Of course, and the main question we want to answer also is how do we get good templates in the first place? So that's why we introduced tracking holistic object representations, for short THOR. So this I showed before, and what we do is we have the tracker predicting the bounding box, and what we do is we plug THOR on top. So, and the only requirement on the tracker is that it's using a dot product to compute the similarity in feature space. So this is all we need, and this is basically what all current trackers are doing. So what we do then is we take the prediction in and accumulate, take this as a template, accumulate it in the short-term module and the long-term module. And there we accumulate templates based on different characteristics. Then we have several templates. We compute the dot product with the new input image. Then, of course, we get several activation maps. Then we do a modulation to refine the activation maps with all the information that is present. And then we get, of course, several bounding boxes. And from one of these bounding boxes, we need to pick which one we use for the final prediction. And we have 4 different modules, and now I want to look into detail into each of them. So first one, long-term module. This is the main piece. That's the most important part. So if you want to accumulate templates over the whole sequence. Of course, like the naive approach would be, we just take all templates and use whatever is like at the highest confidence. However, obviously, a naive approach doesn't really work well. Like you have memory constraints, you have slow inference speed, not to speak of drift. So this just takes in whatever and doesn't care about drift. So obviously this doesn't work. So our idea is we just store a template if it actually contains additional information, and we take one assumption. So the templates, we want them to be as diverse as possible. So of course, this raises the question, how do we get diverse templates? So in this image I showed previously already. So this is what trackers do. You have an input image, template image, you encode this into feature space, compute activation maps of similarities. And now the cool thing is, this network has been trained to compute similarities in feature space. So what we do is, we take these inputs and switch them out for 2 templates, and we encode them in the feature space, and we compute the dot product. What we get is not an activation map, but just a single value, a scalar, which tells us how similar those 2 templates are. So now, if we do this with all templates in memory, we can construct a cram matrix. So, and where every entry corresponds to the templates with the corresponding indices. So now, if we want to increase diversity of our long-term module, we need to increase the volume that is spanned by the feature vectors in feature space. So to give a little bit of intuition, we start the sequence with one base template, so let's call it T1. Then we continue throughout the sequence to accumulate templates, and they are like at different positions in feature space, so they span a volume in feature space. What we want to do to have as diverse as possible templates, we want to grow this volume. So, and as it turns out, a really nice property of the cram matrix is maximizing the volume that is spanned by its feature vectors is proportional to maximizing the cram determinant. So that's pretty awesome. So we get a new template. If we want to know if it's improving our module, we calculate the cram determinant. And if it's increasing the cram determinant, we take it in. Or if it's not, we reject it as a template. So obviously, we haven't solved the problem of drift yet, because if we get a new template and it's not actually showing the object, looks really different, would obviously increase the volume. However, then we need to put a lower bound on the similarity between the base template that we get in the beginning and the new candidate template. So if they are too dissimilar, we reject them. So, however, as it turns out, that can be too restrictive. So we found that we can't really accumulate good templates. Either we get drift, or the diversity measure or the diversity of the module is not that good, really. So we introduced 2 different strategies. So either we have a dynamic lower bound, where we take short-term appearance changes from the short-term module into account, or we have an ensemble lower bound, where we take the static lower bound that I just described, but we don't put it only on the base template, but on all of the templates that we previously accumulated. So it turns out that both of them work really well and have different trade-offs. So on to the next module. So this one, the short-term module, is to handle either partial occlusion or abrupt movement. So in both of these situations, these templates would look too dissimilar, so we reject it by the lower bound. Obviously, we still want to be able to track well in these situations. So, and the short-term module is super simple. We just have several slots, and it's allocated in first out manner. And basically, we also get the cram matrix basically for free, and this we use for calculating the diversity measure for the lower bound. So on to the inference strategy. This is modulation and SDLT switch. So first off, modulation. The goal now is we have information from several templates that we accumulated previously, and now we want to use this or combine this information somehow in our prediction. So what we do is we have the activation maps. We calculate the spatial average over all activation maps and weigh them by their confidence. And then we modulate every activation map with this again. So this is basically refining every predicted activation maps with the information that we have in all the activation maps. So the STL2 switch, the default is we use the bounding box that we predict by the short-term module, since this is able to handle short-term change. However, if then the bounding boxes of short-term module and long-term module are too different, we switch to the long-term module, and then we reset the short-term module. And too different means this we can measure by intersection over union, and we just treat the long-term module as the ground truth, since it's more stable. And when the short-term module goes too far away, then we switch. So on to experiments. So this I showed previously, and now you see that Thor is able to track in this situation really well. And on the right, you can see the accumulated templates in the long-term module. And you see it's able to handle this well and also accumulate really diverse templates. We also did a proof of concept of our idea of the cram determinant. So here you can see what we did is we run a sequence once. At the end of the sequence, we save all templates, then we load it back up again, run it again. And you can see that over several runs, then the cram determinant increases and converges. And actually, in most cases, then the tracking performance also increases or gets better in general. And this actually shows that the cram determinant is a really good measure for determining if the templates are good or not. So we did also benchmarks. Here I focus on DOT 2018, since this is the most important one. And here, performance is measured in EAO. And as I said, Thor, we want to plug it on any tracker. So what we did is we evaluated on 3 different kind of trackers, which are CMFC, CMRPN, and CMMask. And so here you can see those are the results. And the gray one is the tracker only, and the blue one is Thor on top. And like everyone working on tracking knows that like this is quite a significant improvement. Cool thing is we didn't do any training whatsoever. We just plugged Thor on top and run it. So we squeeze out as much information as we can throughout the sequence. And also now, Thor is also current state of the art together with CMRPN. It's actually running 3 times faster than CMRPN++, since it's using still an AlexNet actually. So pretty simple architecture, and that's why it's much faster even. So this also to speed, so also a problem obviously of multi-template tracking. CMRPN on the left side, Thor CMRPN on the right side, and you can barely notice a difference. So there's a really low decrease in performance. CMMask was recently introduced. They just add another branch which predicts a segmentation mask. In this case, again, the cup, our favorite sequence. And we can also just take Thor and plug it on top of these approaches. So to summarize, these are all the points that I raised previously, and we address all of them with Thor. So how do we get good templates? We propose the novel diversity measure. It actually is only a rather minor impact on speed. It's not really specific to the tracker. It only requires that we use a dot product to compute similarities. We don't do any training. All templates can be visually inspected, so that's really nice. You can look at the templates as you've seen and see if it drifted or if it's actually updating and has diverse templates. So we only have 4 simple modules that are actually really easy to implement, and only 4 hyperparameters for this whole system. And also our experiments show really that the long-term module is really highly robust. Okay, at the end I want to mention that the code is open source, and also thanks to my collaborators. And if you have any questions that I can't answer in the session, just feel free to write us on Twitter or by mail. Thank you.
Okay, any questions before we break for? Right here.
I don't know enough about it to understand if you use a common set of training data for your mapping from image patch to feature vector, or where did you get the training data? Is it data specific to the problem, or do you use a standard data set?
Yeah. Like usually trackers, as you've seen previously in the previous talk, Usually you have like data sets on that you train, and then you have test sets that you have never seen before. But as I said before, this doesn't really matter for our approach. We just take the network from the tracker that is given to us, which is trained on some data. We don't really care about this, and use it to compute similarities. In this, yeah.
But you're assuming that the feature vector is meaningful for that particular object you're tracking at runtime.
Yeah, true. The feature space needs to make sense for tracking in this case, of course. Yeah.
So there's a variety enough in the standard training data set for tracking general objects?
Yeah, that's the goal of general tracking approaches, yes. So, of course, the data sets needs to be as diverse as possible so you can actually train this meaningful mapping, yes.
Thank you.
You're welcome.
Any questions from room 104?
No, there's nothing on this side.
Any further questions? Here's one. There.
Thanks for the talk. How does it work with how does it work with tracking multiple objects or multiple instances of the same or similar objects in the same frame?
That's a great question, yes, and that's actually what we're looking into right now. So that's we started now with single object tracking since it's obviously the easier task, but you can think of just extending this, and also I don't want to give too much details, of course, but yeah, you can easily extend it to this this setting, yeah.
Okay, thanks.
Any further questions? Okay, we are running a bit late, so I think to give you a chance to get a coffee. We're going to. Can we thank Axel again and again? Congratulations once more. Thank you.